Pre-Cal, welcome back to part 2 of this magical video, and we are picking up right where we left off, and we are finding the zeros of this quartic function. The first thing I'm going to do is graph it. So we need to input it on the y equals screen correctly, 2x raised to the 4th. Be sure your calculator is charged. Be sure you know how to enter in a function properly. So 2x to the 4th plus 3x raised to the 3rd plus 3x minus 2. So here's our function, and when we graph it, hopefully we're going to see some zeros. Yep, I see 2. I see one at -2, and it looks like there's another one at 1/2. Remember, we can trace on the function, or I like to use the 0 on calculate. So we can find a 0. We see this one's at -2. Let's find out where the 1 is to the right of the origin. So I've got a left boundary, and then I need a right boundary. So it's going to look in that little slice, and we have another 0 at 1/2. So we can see 2 zeros, one at -2 and one at 1/2. So these are some values that I'm going to be able to depress the polynomial with. So I've got one at -2 and I have one at 1/2. We are looking for 4 zeros total. And it appears that my other 2 zeros are going to be imaginary. So let's go from here. So using one of these, remember, these are the roots or the zeros. The factor that would yield -2 is x plus 2. So this is a factor, and -2 is a root. I've got my root outside the box. Inside the box, remember, I need every power of x represented. So we are missing the x squared. So I'm going to put that in as a 0. 2x to the 4th, 3x cubed, 0x squared, 3x -2. I like to draw a line right there because I'm going to get the remainder there, and I am anticipating that the remainder is 0. It better be 0. So bring down that 2, multiply and add, multiply and add, multiply, and we get -1. -2 times -1 is +2. -2 plus 2 when we add is 0. Hooray! Now, let's keep going. We also know that 1/2 is a root. So 1/2 is the result of 2x minus 1 as a factor. So we're going to divide by the 0, 1/2, same process. And remember, we depressed it down once, so now we should get a remainder of 0 here. Bring down that 2. 1/2 of 2 is 1. -1 plus 1 is 0. Half of 0 is 0. And that's 2, and that is 1, and there we go again. So we end up with this particular polynomial left. We started with x to the 4th. We depressed it down first, then second. So we've depressed it down 2 powers. So what remains here is quadratic. So we have 2x squared plus 2 equals 0. And this is the quadratic equation that we now want to solve to get those last 2 roots that we're looking for. And we know they're going to be imaginary. So if we have 2x squared plus 2 equals 0, we can factor this, or we could just use the square root property. Let's do that. -2 minus 2, 2x squared equals -2. Divide by 2, divide by 2. X squared equals -1. From there, square root, x equals plus or minus I. The square root of -1 by definition is I. So our 2 missing zeros are positive I and negative I. 1, 2, 3, 4. 4 roots. We just found all the zeros. The first 2 are real. The second 2 are imaginary. Last problem. Given f of x equals 2x cubed minus 7x squared plus 9x minus 3. Use the remainder theorem to find f of negative 10. Now, you could plug in negative 10, and that would probably require the use of a calculator to help you get through it. But the remainder theorem says this: we can use synthetic division to evaluate functions, because if we divide by the factor x plus 10, then we should get whatever the remainder is will be equivalent to the evaluation of f of negative 10. So let's give it a shot. 2x cubed, 7x squared, 9x minus 3. 3, 2, 1, none. They're all there. 2, negative 7, 9, and negative 3. We are after the remainder. Bring down negative 10 times 2 is negative 20. Negative 7 and a negative 20 is negative 27. Negative 10 times negative 27 is 270. 9 plus 270, 279. Negative 10 times 279 is 2,790. Negative 10 times positive. And then finally, add those together, we get negative 2793. So, f of negative 10 is equivalent to that remainder. It's the evaluation of the f function when x equals negative 10. So, negative 2,793 by the remainder theorem.